Hi class, I am Professor Musi from Rhodes College. Have you ever had difficulties with significant figures in your chemistry calculations? In this video, I will try to help you understand the nature of significant figures, or sig figs as we call them. I think once you understand what significant figures are, you should be able to handle significant figures in your calculations easily. As the name implies, significant figures are the numbers that hold significant values in a given measurement. So, the first thing we will do is to look at some quantitative measurements. When we study quantitative measurements, we will use accuracy and precision to describe the quality of the measurements. Let us look at this mass scale and try to read this as accurately as possible. And you see, this is the indicator. Here are some readings done by several students for the same mass indicated by the scale. So let us see which readings are correct. When you read a scale like this, first we need to look at the calibration marks. Now here we have long calibration marks and short calibration marks. Long ones indicate increments of tens, right? And the short ones indicate 1 kilogram increments. So in between these small lines there are no calibration marks. So what we need to do is to estimate the values in between them. Let us read the scale: 10, 20, 30, 40, 50. Now we can count the short lines: 1, 2, 3, 4, 5, 6, 7, 8. It is 58. But the indicator is between 58 and 59. So we have to make a rough estimation between 58 and 59. Let us see. I read it as 58.4 kilograms, but you might read it as 58.5 kilograms. Both these measurements are correct. The first two digits are certain. It is the last digit that is uncertain. So in this case, the last digit of the measurement is uncertain. All experimental measurements inherently involve some uncertainty. Now, these three numbers describe important information about this measurement. The first two numbers, 5 and 8, are certain, and the last digit 4 is uncertain. These are very significant information. Therefore, all these three numbers are significant, and the measurement has three significant figures. Usually, the first significant figure in a measurement is a non-zero digit. Let us look at these readings. Choice A is not valid. The indicator is clearly beyond 58.0 marking. Choices B and C both are correct. Choice D is incorrect because it suggests that 0.4 is certain, which is incorrect. In other words, it also suggests that there are clear calibration marks between the short markings. And you know it is not true according to this scale. Now let us make some mass measurements using the electronic balance. Now we are in the chemistry lab. We are going to use two types of electronic balances. This one is a top loading balance, and this one is an analytical balance. Now these images show the mass measurements obtained for the same object using the top loading balance and the analytical balance. Here, for this mass measurement, we have 4 significant figures, and the uncertainty is at the 100th place of a gram. And for this mass measurement, we have 6 significant figures, and the uncertainty is at this place, that is at the 10,000th of a gram. So obviously this balance is more sensitive, and therefore it is more expensive than the top loading balance. Now I am going to measure the mass of this aluminium cube several times using this top loading balance. When you use the balance, the best practice is to use a clean beaker or a weighing paper or a weighing board to hold the object that you measure. If we spill something on the balance, we should clean it immediately. That way we can avoid damaging the balance. Now I am placing the metal cube gently inside the beaker. The mass is 21.80 grams. I will repeat the process 4 more times, and I am recording the data in my lab notebook. These are the 5 replicate mass measurements I gathered for the aluminium cube using the top loading balance. As you see, they are slightly different from each other due to the uncertainties associated with the balance. We call these small deviations random errors. Random errors are impossible to avoid in a given experiment. So, what is the actual mass of the cube? The average or the mean of the experimental data is considered as the best estimate for the true value. So average is calculated like this. We add all these values and divide it by the number of data points. Your calculator will give you something like 21.794. But the average should have 4 significant figures because our original measurements have 4 significant figures. N is the number of data and xi is the any given data point. What do we do about these random errors? Scientists report these deviations as standard deviation, which is calculated using this equation. So I'm going to show you how to calculate the standard deviation. So right here I have this value calculated in this column. Xi is any given data point. Xi minus x bar means the difference of this value and the average. So for the trial 1, xi minus x bar squared is this. Summation of xi minus x bar squared is 0.0004. N is 5, n minus 1 is 4, and then take the square root of this. And this is the standard deviation. The standard deviation has the same units as the mass. Usually we can calculate the standard deviation using a calculator or Microsoft Excel or similar spreadsheet program like this. Here I have calculated the mean, the average or the x bar and the standard deviation using the Excel. The standard deviation informs us the uncertainty associated with this mean. So we always report the mean with the standard deviation like this. Now we have the mass of the cube determined to 4 significant figures. The standard deviation 0.01 gram is the uncertainty of the balance. The uncertainty of the balance is usually known. Therefore, we measure the mass of a given object only once. But this exercise has helped us to understand the important aspects of a given measurement. Now let us carry out the same exercise using the analytical balance to understand its uncertainty. Now we are in the lab again. I am about to take the mass of the cube using the analytical balance. The balance is very sensitive, so we need to close all the shutters completely. The mass is 21.7974 grams. Now we have recorded 6 significant figures for this mass measurement. These are the mass measurements that I gathered for the aluminium cube using the analytical balance. I calculated the mean and the standard deviation. Now, how many significant figures should I have for the mean? In fact, the real rule of significant figures comes from the standard deviation. All these leading zeros in the standard deviation tells us that the values at these places of the mean are certain. That means there are no uncertainties at these places. The place at which you have the first non-zero digit has the uncertain digit or the last significant figure. Here in this case we have our first non-zero digit at the 10,000th place. That means this is the value that is uncertain, provided that the balance can measure the mass up to that point. And we know that the analytical balance can measure the mass to 10,000th of a gram. Therefore, we should round this up to 6 significant figures. So our mean is 21.7976 gram. This understanding also answers the popular question about the number of significant figures one should keep for the standard deviation. We pick the first non-zero digit of the standard deviation. Here the uncertainty occurs at the fourth decimal place and we round it up to 0.0002. So we report our final result as 21.7976 plus or minus 0.0002 grams. Now let us compare our data from the two balances. The analytical balance has produced a smaller standard deviation. As you see, the data changes only at the fourth decimal place. Therefore, the measurements from the analytical balance have higher precision than the measurements from the top-loading balance. Precision describes the agreement between replicate measurements. Higher the precision, the closer the measurements are to each other. If there are only random errors, the mean of the data represents the true value. In fact, what we see here is a range for the experimental true value, which is defined by the mean and the standard deviation. If there are non-random errors or in the presence of systematic errors, accuracy will be compromised, like in this picture. For example, not leveling the balance properly is a systematic error. Systematic errors can be eliminated. Therefore, we calibrate our instruments regularly to eliminate systematic errors. There are two types of volumetric glassware. Glassware marked with TC are calibrated to contain a certain volume accurately. The ones that are marked with TD are calibrated to deliver volumes accurately. Volumetric flasks are calibrated to contain precise volumes. For example, this 25 milliliter flask can contain 25.00 milliliters at 20 degrees centigrade when it is filled to the mark. It has a tolerance or uncertainty of plus or minus 0.03 milliliters. Volumetric flasks come in different sizes and different tolerances. We calibrate our burettes to deliver volumes precisely. One must record the burette reading to the 100th of a milliliter. Here, the burette reading is 21.31 milliliters. Another instructor may record it as 21.30 milliliters. Either way, your burette reading must have two decimal values. Measuring cylinders and beakers are not suitable for quantitative volumetric work. They do not have the high precision necessary for quantitative analysis. Now, let us review what we learned. Significant figures inform us of the certain and uncertain digits in a measurement. All measurements have uncertainties, and replicate measurements reduce these random errors. Experimental true value is a range defined by the mean and the standard deviation of replicate measurements. The first non-zero digit of the standard deviation determines the last significant figure of the mean. When we make measurements using our lab instruments, we must record the correct number of significant figures. For example, if we make a solution using a 50 ml volumetric flask, we must record the volume as 50.00 milliliters. And if we dispense a liquid using a 10 milliliter transfer pipette, we must report the volume as 10.00 milliliters. Thanks for watching this video. I hope now you understand the nature of measurements and the importance of significant figures. Please feel free to contact me if you have questions or comments. My next video is about the importance of significant figures in problem solving.